All right, physics. Let's do a thing. I feel like it's been a minute since we've done something here, but we are third mark period, so that's weird. I don't know how that snuck up on me. It's all good. Um, oh, one thing to note: while you're watching this, there should be keyword should, a quick five question, five-ish, maybe six. I don't recall exactly how many questions, but a quick quiz on my CBA on momentum, right? We did the questions on momentum from before. Y'all finished the lab for momentum not too long ago. I haven't graded quite all of them yet. I've gotten through a few of them. I'll finish posting the grades once they're all definitely graded. So, we have one more topic that I want to talk about in between now and the Christmas holiday. And after that, we will get into a little bit of review, a little bit of like connected questions, and a few concepts that I just think are nice because I like classical mechanics. That was very much the class that I enjoyed the most in college, and I think it's the topic that kind of applies the most because it's the one that you can see most readily in everyday kind of stuff. So, the last topic that we are going... Oh man, I gotta... Okay, there we go. I had to get to my drawing pad. So the last topic that we are going to talk about here is... I don't like the size of that pen, so we're gonna change it. Energy. This is kind of a big deal, all right? Energy is something that you can kind of use for a lot of stuff, and it will get you out of being stuck, hopefully. But energy is kind of a weird like concept, and it came up today towards the end of class. Somebody had asked like, "How do you know energy is a thing?" Well, yeah, no, that's a good point. Um, when we talk about energy, we talked about it last year, just like in terms of conservation of energy. All the energy in the beginning had to be there at the end, and a lot of it was like chemical potential energy that turned into heat and light energy, or it was like thermodynamics. We talked about how much heat is produced, how much heat is absorbed, so like heat energy. Hopefully you remember from last year that the units are joules, which is capital J is just the abbreviation. Um, every kind of energy is measured in that. So when we talked about heat energy last year, it was measured in joules. When we talk about energy this year, it'll be measured in joules. All right. There are two major types of energy that we're going to talk about, and they will always be conserved like before and after an action. They might transfer from one object to another. I talk about energy, and I don't know if I said this during class today, but I'll be sure to mention it to the Group 1 kids on Wednesday. Energy is like the currency of the universe. If you have it, you can do stuff. If you have a lot of it, you can do a lot of stuff. If you only have a little bit of it, then you can only do a little bit of stuff. But the two different types of energy that we're going to kind of focus on are potential energy and kinetic energy. Right. Now, hopefully you remember kinetic energy, specifically average kinetic energy. That should spark some kind of memory or maybe nightmare in the back of your head. The average kinetic energy of an object is how we define the temperature, right? Temperature is a measurement of the average kinetic energy of the particles in an object. What we'll talk about a little more this year is that potential energy is the energy that you have stored, and it might be stored within you, like literally as the chemical potential from your food. It could be energy that's stored because of where an object is. Like if I lift a bowling ball up over my head, then I'm going to give it a bunch of potential energy it could do stuff with. Kinetic energy is considered the energy of motion. So as things are moving, they have kinetic energy. If they stop moving, they stop having kinetic energy. Both types of energy that we're going to talk about, again, potential and kinetic, they both depend on mass, right? So PE is how I'm going to abbreviate potential energy. It equals mass, right? M for mass. But also, I use the bowling ball as an example, right? It also depends on height. A bowling ball will do much more damage. It has much more potential, right, to do things, to break stuff particularly, if I lift it up over my head versus if I had it near my waist, right? So it also depends on the height. Height above, I'm going to put this in quotation marks, the floor. Right, the floor is how you define it. It could literally be the floor of your room. It could be the desk. The desk could be considered the floor in the context of like, that you guys can't see it, but I have a desk that's in front of me. So if I held a bowling ball here, it's over the floor. If I hold it in front of me, it would be over the desk, and that would have a different amount of potential energy. I would be measuring it just from the desk. That's the first interaction that we'll have. I've left a space here because the reason that the bowling ball has potential energy when I raise it, and if you remember, this is lowercase g, this is the acceleration due to gravity. Right? So the potential energy of an object is m times g times h. It's mass times the acceleration due to gravity, which is a constant. It's 9.81. If you forget, it's on the front page of the reference table. Times the height above whatever you're defining as the floor. Okay. An object doesn't have to be moving to have potential energy, but it could be moving and have potential energy. The object has to be moving in order to have kinetic energy, which I'm going to define as Ke. There's a half in this equation, and there's a squared in this equation, so be super careful. This is mass v for velocity, as it usually is. Now both of these end up with the units joules. But these are your two base equations that we're going to be looking at. Conservation of energy doesn't mean that the amount of potential energy and the amount of kinetic energy will always be the same. It means that if an object has a certain amount of energy and it changes where it is or what it's doing, then it should have the same amount of energy that it started with. So if I have a bowling ball on a hill, at the top of the hill, or if I hold a bowling ball in the air, right, as I'm holding it up above my head, it has a specific amount of potential energy. When I release it, that potential starts to disappear because it converts into kinetic. So halfway down, half of the energy should still be potential. The other half should now be kinetic. All the way down, right in the instant before it hits the ground. It should have basically zero potential energy because h is 0, it's right on the ground, and it should all be kinetic. So all that potential from the start, once it's right about to hit the ground, turns into kinetic energy. Right? A quick example, a quick easy example of just showing you the equations really. These two types of energy, by the way, are generally referred to as mechanical energy. We have thermal or thermal energy, heat energy, right? We have electrical energy, we have nuclear energy, but we're going to talk mostly about mechanical energy, which is potential and kinetic. Technically, there's a third type of energy, heat. And this is the, this is where, like, lost energy might go to, right? If it looks like something has lost energy, it probably turned into heat. The reason we call it lost is because we can't, like, recapture it and use it for something productive. It's just, it's gone. Once car engines are notorious for this. Most car engines are no better than like 30% efficient. So all that gasoline that you put in your car, let's say you have a 10-gallon tank. I'm doing that for ease of numbers, right? 10-gallon tank. If you used all 10 gallons of fuel, only 3 gallons were actually used to move your car. The other 7 gallons were lost as heat, which is unfortunate. Internal combustion engines are wildly inefficient. Anyway, it's like a side note, right? But an example might be that a goose... Oh, we need a... okay. How big is our goose? Should probably be pretty big. It can't be like super big. Let's call it a 12 kilogram goose. Flies at 5 meters per second at a height of 40 meters. Right, I might ask what is its kinetic energy? Right, and might ask what is its potential energy? And I might ask what is its total mechanical energy? Right. Again, these are all just, for lack of a better term, plug and chug. You plug in the numbers, you crank out an answer, right? So kinetic energy would just be 1/2 mv squared, which means it's 1/2 times 12 kilograms times 5 meters per second. I'm going to square that, which is half of 12 is 6, 5 squared is 25, 6 times 25 is 150 joules of kinetic energy. Straightforward enough. Potential is m times g times h, which means 12 kilograms. G is 9.81 meters per second squared, and h is 40 meters. And that's going to be give or take 40... I think it's about 4,700 joules of potential energy. 47... I'm going to do some exact math here. If I can find my calculator. 12 times 9 nope, just kidding. Not 90. 9.81 times 40 is 4,709 joules. I'll round to the nearest whole number. So 4,709 joules. The total would just be add them together. So I'd get 4,859 joules of mechanical energy. Right. And again, that's a super straightforward example, but I wanted you to have it. I wanted you to see it. We'll continue doing more, but I'm not going to give you any practice questions tonight because I want you to do that quiz. Make sure you do the quiz, and we'll do some more examples with energy on Wednesday, specifically with conservation of energy. I'll probably come back to our goose. All right. I will see you the next time. In the meantime, make sure you finish that quiz. That's really all you got. All right. You'll have some more energy questions to do after Wednesday's class, or after the B-Day class, whenever your class is. But we'll talk more then. All right. Take care, y'all.